Okay, we're gonna do some beam deflection examples today at the end. We did have the 2 lectures on beam deflection; those were pre-recorded, and I thought I'd do a couple of examples, or maybe just one example of beam deflection. Before that, though, we are gonna do the intro to the Truss project. So let's look here. Is this the right spot? Yes. Oh, well, except let's make it fit on the screen. That doesn't quite fit, does it? That works better. All right. So here, Truss Project Summer 2023. It's going to be a PDF describing the scope of the project, what you need to do. 3 or 4 people in your group. It is a group project. Now, you're not probably all in the same spot. You know, you could be scattered around anywhere, really. This is an online class. So if you can't get the 3 people in your group, then let me know and we'll figure something out. But the idea would be that even if you're remote from one another, you could still work on this project. It doesn't require any actual fabrication like it would during the regular school year, where we would go and, you know, we'd laser cut pieces of the material that we had been testing in lab 1 and lab 2, and we would use that material to, usually it's design a truss, like a truss bridge, and then test it, you know, predict what it's going to do and then test what it actually does. So since we're not in person, it's slightly different. We won't actually fabricate a truss. You don't even have to design a truss bridge. You just design a truss of some site. It doesn't have to be, you know, flat pieces made to look like a little bridge. It can just be, as long as it does have to be a truss, and it does have to be a statically determinate truss. I don't know if you remember what that means or not, but it means that you don't have too many pieces coming into a single joint. So like if you had a single joint with 5 pieces coming into it, 5 members, then that's probably going to be a statically indeterminate truss. Basically, let's see, there is an equation if I can think of it. You have, let's see, 3 external reactions, right? So those equations are needed to calculate the external reactions. There's usually only 2, but you could have a third one in the X direction, so like a pin and a roller. And then each member, well, not each member, each joint has 2 reactions. Like if you look at a method of joints and look at every single joint in the truss, you could create 2 equations. So basically you can create the number of joints times 2 plus 3 reactions, number of equations. If you ever have more members than whatever that number is, then you can't solve for all of the member forces. So well, actually, I guess you have to, yeah, there's something like that. I'll have to look up the exact formula for the equation, but it can end up that you have too many members for the number of equations that you have to solve the truss. Doesn't matter if you use method of sections or method of joints or any of that, you just have too many equations. Now, you can still work with those trusses, just not with the methods that we did in this class. Those trusses are classified as an indeterminate, well, statically indeterminate, meaning that you have to use energy methods or something else in order to calculate the member forces. And we didn't talk about any of that. That would be, if you take the class after this one, that would be when you would figure out how to do those calculations. So you do have to make a statically determinate truss. Let's just look real quick and see if I can quickly find the equation. Let's see. Well, that's useful. Yes, it is only. It references the equation right here. But the idea is that using only statics. So I wish it would actually give the little equation there. It doesn't. Let's see if this one gives the equation. There it is. All right. So And now these are talking about planar trusses also. Where in your project, you don't have to have a planar truss, but that does mean that then you have to figure out how to do three-dimensional joints, which we did. Three-dimensional concurrent force systems, and a three-dimensional joint of a truss would be just like that. But here's the equation. So B is the number of truss members. I don't know why it's B, but number of truss members is B. R is the truss reactive forces. That should be 3 most of the time, because most of the trusses in statics are going to be supported by a pin and a roller in 2D. So the pin gives you 2 reactions, the roller gives you 1 reaction, so that gives you a total of 3 external reactions. And then J is the number of joints or pins on the truss. And then B plus R, so that's the number of members and reactive forces, equals 2 plus J. Now it actually could be less than that, I believe. So not 2 plus J, 2 times J. So that's the 2 equations you could write for every joint, the 2 concurrent force systems for 2D. Again, this is planar. I said somewhere in here, yeah, planar trusses. Then if that equation is true, or if the B plus R is less than 2 times J for some reason, then it would be statically determinate. So you do have to have that qualification in your truss. The objective here is to design. So you'll design in Solidworks on paper, analyze. So that means do the method of joints, method of sections, and simulate. So that's probably Solidworks, a truss. So you could even see where you have to do these 3 pieces plus write up a report. You could see how you might start dividing up the teamwork, labor. It's tougher to work in teams when you're not right there, but you could figure out a way to divide the work evenly. I don't think I'd recommend having one person design, one person analyze, one person simulate, one person write. That would probably not go well, because there's just not as much interaction in the team. So you're essentially just doing your little section and not really having any input to the other parts of the team. But you could have one person responsible for the design, and so the group could come up with the design, but one person is responsible for recording it and maybe generating it or whatever, but still have the whole group interact on the thing. You're going to have a written report as the deliverable. There won't be an actual fabricated truss. These are the sections that are going to be in your report. You'll have title page, just a regular thing, abstract, executive summary, so like 200, 300 words that describe what you did and the major outcome of your findings. So maybe some major simulation results. Design objectives. What are you trying to do? So I, in this case, am not telling you other than you have to design a truss. You're putting the context, your team is putting the context of why this truss needs to be designed. It could be that it's a little, a bridge you're designing. It could be stadium lighting. It could be a bicycle frame, a lot of different things. It doesn't have to be super realistic or super complicated. It needs to be more than a triangle. So technically a triangle, I guess, would be a truss, but it needs to be a little more than that. But it doesn't have to be overly complicated. But why is your team designing this truss? You don't have to use any particular material, so you choose the material that you're going to use. I would say that it's probably best to use a single material instead of trying to have some pieces that are wooden, some pieces that are metal. The wood is actually going to be a problem in SolidWorks because it's not going to simulate actual wood, how it would behave. So use a metal, use a steel for your truss, probably, unless you're trying to do some kind of fancy bike frame and you want a really lightweight metal. But use metals, ductile metals. Come out with a couple of design alternatives. So you've got your scenario of why you're designing this truss, then describe, without going into super detail, maybe you have a sketch of the truss or whatever, different alternatives that could solve this problem. And then one of these is the one that you actually are going to fully design. Justify why the other three are not suitable. You know, they're too much material, they're not statically determinate. You know, maybe there's some, you know, whatever reason, each one of the other designs doesn't get chosen for the full design. So this little section will basically be a couple of figures that show the alternate designs with a paragraph about each one saying why that design was chosen or was not chosen. Your design calculations, so use by hand or MathCAD, but this is not the Solidworks part. Analyze the truss. So if it is something like a truss bridge, you don't have to analyze both sides. You can assume that it's perfectly evenly balanced and you only are analyzing one side of it, and the other side is exactly the same, whatever. But by hand, show your calculations on member forces, you know, things like that. Free body diagrams. So this is a longer section here. Do not, in this section, go through every individual. Let's say you use the method of joints and look at every joint. Don't go through every one of these. Show an example of what you're doing, and then the full set of calculations goes in the appendix. So you do one example of how you're doing the free body diagrams and how you're doing summation of forces in X and Y and all that kind of stuff. Maybe you show one with calculating your external reactions, but the full set of every joint goes in the appendix. Make sure you include free body diagrams. Then put your truss in Solidworks. Now, different groups are going to have different skill levels at this, for sure. At the minimum, draw a one part, you know, extruded one part version of your truss and load it up and simulate it. That will not be a great simulation, because if you don't actually assemble the pieces like pins, then it's not going to behave quite the same way that your truss calculations are going to say it's going to behave. But that will at least get you by. Now, if you know how to do assemblies and simulations of assemblies, then do that. You can actually, if maybe you don't have rectangular cross sections, you can define members. There are truss elements you can use in SolidWorks. I think I will give one little demo of that later, once we get closer to the end of the quarter, in case you're interested in. But at the minimum, if your team just doesn't have a lot of SolidWorks experience yet, then just do a single extrusion and simulate that, and we'll be okay with that, because everybody's at different levels on how much they can do with SolidWorks. I've even had several questions about Lab 1 and Lab 2, well, mostly Lab 1. I did move the due date again for Lab 1 to give, I saw that, you know, 2/3 of the people had submitted it, but there were a couple that were still having trouble, so I moved it a couple of days later to this week. Then a little bill of materials. This would be something that looks like a database, so a spreadsheet, Excel, and it's a list of the parts that you would need if you were building this truss, whatever size the thing is supposed to be. You don't actually have to go do it, but where would you get these parts? You know, Online Metals, McMaster Car. Where do you get these parts, and how much do they cost? How many of them do you need? That kind of thing. You don't have to be super detailed on trying to figure out like how the nuts and bolts of everything. We are going to simplify it. You don't have to figure out welding cost if you're trying to weld something. We're going to keep it on the simpler end here. Also, if you're using, think of the potential, there may not be any, but the potential environmental impact of choosing these particular materials for this application. Maybe there is, maybe there's not. Now, there is something, but maybe it's not significant. But consider it and explain what you think about it. Then there's a little conclusion here, you know, lessons learned, what you figured out. Maybe you analyzed it and everything and simulated it, and it just won't work. That's a possible solution, you know. Put that in your conclusions. Put any references you used, text or web-based references. Any sets of appendices with drawings of the full thing. All of those joint calculations from earlier could be in the appendices. I've got a rubric here of what you will be graded on for when you turn this thing in. It is a team grade, so you'll share the same grade for this. This rubric is in Moodle. I did put it here. It may be really small to see, though, if you're looking at it. Although this looks readable here when you're on the computer, but if you print it out, it might be kind of small. But this is the rubric that's in Moodle, and that all of that information is in the document called where is that? Truss Project Summer 2023. So that's all right there. These other two, these are links to MD Solids. MD Solids is it's not updated any longer, but it is a piece of software. I think they offer it for free now. It used to be paid, but I think it's free now. And it will do things like statically determinate truss member calculations. So you can check your hand calculations for the force in members. It'll do moments of inertia. It'll do buckling. We haven't really talked about buckling yet. It'll do a lot of different engineering, particularly statics and strength of materials type basic calculations. And it's a decent piece of software, and it's free. There are online versions of this kind of thing also. So you could use one of those maybe in your design alternatives to quickly calculate some rough member forces. It won't tell you anything about the member is going to fail or not. It doesn't have that built into it, but it'll tell you forces in the member. So that's a link. This one is same thing, but for buckling, which we haven't talked about yet. We'll talk about that later. So that's an overview of the Truss project. So everybody that's going to stay in the class should be in the class now. We're past the drop date. So you can form your teams, and it would be good to let me know who's on your team just so I can keep track. And if I get emails about people who are looking for a team, I can start to, you know, let the rest of the class know. Use Discord to find teams, whatever you want to do to find the teams. But look for 3 or 4 people on a team as the ideal number. 3 is probably the better number, but 4 will work fine too. 2 is pretty small. 5, you're going to end up with people not really contributing at the level you would want them to. So I would do 3 or 4 people. All right. I don't see any chat questions about that, so if I see any pop up, we'll come back to that. But what I was going to do now is do some beam deflection. So let's go to find a beam deflection equation or problem. Those might be in the optional 3. Let's see. I don't remember where they're at. No, that's torsion. So I think they're in optional 2. All of the, looks like all of our homework is closed now in WebWork. There will be stuff opening up. There won't be any, I don't believe, opening. Actually, I think I will open one for the beam deflection just because we're just now talking about it again. If I can find where the questions are. I didn't want to do that. That's a beam design. Let's see where they're at. These are all the flexural stress. Maybe I don't have any. beam deflection problems in the optional. Let's see. There's a shear and bending diagram, but that's not actually what I want. Well, all right. We may just have to create our own, but it could be maybe in homework 17. This is one. All right, so that one, I want to do more than just that. Maybe this one. This is an interesting one. All right, so this is one of your actual homework problems, but that's okay. If I can get it copied. Can't get it to copy for me. Well, I'm not sure. Let's see if we can find our tool. There we go. All right. So we're over here. And this one, I don't remember how much you might remember from the beam deflection. It's been, a week since we did anything with beam deflection. But the idea is you could go in and write what's called the equation of the elastic curve. So you could write it from scratch. Integrate the beam to figure out the loads that are on it and everything, and actually go and do that. But there are references that have done that for you. Let's see if we can find one of them. Let's see. I think I have one in the reference material folder. Maybe not. Well, there'll be some in the exam references, so we'll get one from there. See if I can find it. It must be in exam reference 1. There it is. All right, let me get it copied over. So this is the one from your book, table A19. It's a little bit scratchy because it is a scan from who knows where. All right, so we'll put it off on the side over here. All right, so this is a set of references. Actually, I might need to put it below and make it bigger because it's really kind of small. All right, that looks more readable, I think. All right, so these are 8. I kind of cut off the bottom one. Maybe we won't need that one. These are 8 different cases. 4 up here are the top ones are cantilever beams, and the 4 at the bottom are simply supported beams. And I actually think we do need this bottom piece. We'll have to go chop it off and add it to our list here, because I think I do need that. Let's get that before I get too far. We'll just plop it in right there. Okay, so the 4 on the bottom, 5, 6, 7, 8 are simply supported beams, and the 4, 1 through 4 are cantilever beams. And all these equations are the far right column for this diagram anyway is the equation of the elastic curve. So if you wanted to know the deflection at some specific point in the length of the beam, not necessarily at the end or the most deflection, but just anywhere in the beam, you would use that equation. The maximum deflection, kind of the middle column here, is where is, all these cantilever beams, maximum deflections at the very end of the beam, but for the simply supported beams, it's somewhere in the middle of the span. Sometimes it's in the direct center, like on case 6 here, but other times it's in some, odd place like this. So it tells you where and what the maximum deflection is. And then this first column of equations is slope. So sometimes you want to just know how slanted is some beam at some point. Usually the slope equations are at the end of the beam. So either the free end for a cantilever beam or the two supported ends for the simply supported beams. You don't really have an equation, at least in this set of beam equations, that tell you slope somewhere in the middle of the beam. So you'd have to go back to the equation of the elastic curve and back it out from there if you needed that. All right, so we've got this little setup. It's kind of got a combination of a cantilevered section BC and a simply supported section AB and one little load on it. It tells us the type of beam it is, so we can go use that to get moment of inertia. Structural steel will tell us its modulus of elasticity. Both of those things are going to affect beam deflection. Then we have some dimensions, a force. We are neglecting self-weight, so that means that we're not worried about the beam bending under its own weight, or at least we're not going to calculate that. If we wanted to calculate that, it would be a evenly distributed load all the way across the beam, and we'd have to deal with that also. So we want to find the slope at B, so that's where this little roller is. The deflection midway between the supports, so right between A and B at the center of that, and then the deflection at the very end of the beam. So we don't have, that doesn't exist for any of these. We don't have a scenario that looks like this. So we're going to have to use what's called superposition, where we take multiple scenarios that we do have, superimpose them on top of one another, and create something that will give us the same effect as what we've got here. So what would help is if we draw this thing and kind of get an idea of what is it even trying to do. So we'll go down here and we'll draw maybe here. So there's our beam, and we've got, I think it was a pin over here, and I think we had a roller maybe here, and we had a point load. Let's put our actual size on this. This was for mine, it was 65 kilonewtons. And then we had two dimensions, 6.9 meters and 4.1 meters. Okay. This was the 6.9 meter, and this was the 4.1 meter. All right, and we also knew that this was a I-beam. So it has a little flange on top and bottom, and it was a specific one. It was W406 by 149. So from that, we can get a moment of inertia. We'll have to look that up. I don't have any way to know that offhand. But let's see if it's in our exam well, that's not, but this is. Let's see. Is that the right? Yeah. So while we're here, let's get the modulus of elasticity for structural steel. We are in metric units, so we need the metric elasticity. 200 gigapascals. I don't know if you can read that, but 200 gigapascals is what it says. So while we're here, I'm just going to write down 200 gigapascals for E. Now let's go back and see if we can find I. That means we need a W right here. So we had the W406 by 109. That's right here. And we want the moment of inertia. We want it under the XX column. I don't remember. Let's see. Does our picture give us any indication? No, our picture doesn't really tell us which way the I-beam is going, so we're going to assume it's going the normal way, the ordinary way. And that means that we're going to use XX for our data here. 406 by 149, 620 times 10 to the 6, so 620 million millimeters to the fourth. Okay, so we can go back to, where did I write those down at? Here they are. 620 times 10 to the 6 millimeters to the fourth. So we have I, we have E, and we have a picture of our beam with some dimensions on it. If this thing were to bend, so it would bend and look something like, I think, this. Well, it wouldn't go that far, would it? It didn't right. Can't erase that piece. There we go. It would do something like that. Maybe I shouldn't have used blue since I used blue for the other lines, but that's what I have. So it's going to bend upwards in the middle of the beam, so tension on the top, and then when it rolls over that roller, it's going to bend downwards. And actually, this little section is going to be curved. So let me get another color here so that it doesn't, we'll do red. So something like that is what I expect it to do. And we want to know a couple of things. We want to know theta at B. So B was which one? B's the roller. So we want to know, let's make these in green maybe. We want to know this, that angle. That's part one. We want to know the deflection of the beam midway between the supports. That's this one. We want to know that distance. And then we want to know deflection at C. That would be that distance. I don't know what we call this one. Delta 1/2, we'll say. It's not really half of the length of the beam. It's half the distance between the supports. What did they call it? Oh, they just said YAB midpoint. All right. So we can do half of AB. There we go. And they're using Y. I use delta. So Y is what the WebWork had. Okay. Well, let's go in the order. I think the order they have listed is probably what we need. So the order is theta B, so the angle at B. Now, the force 65 newtons is causing section, let's get some letters on here, A, B, C. It is causing section BC to bend like a cantilever beam, but it's already tilted. Like it starts out already bent because the hump in between A and B. So we kind of need to know what one of these 8 options here would let us calculate the deflection at B. Or not the deflection at B, the slope at B. And I think what we could do is let's take our beam and treat it like this. This is not quite superposition. Oh, I didn't want that. See if we can make it a little nicer. Or maybe I can just... well, that's good. We'll put our pin and roller. And instead of a 465 newtons at the end at C, let's take and do this. Change that force, 65 newtons, or kilonewtons. Is that right? Kilonewtons? Yes. 65 kilonewtons times a moment arm of 4.1 meters and create a 266.5 kilonewton meter concentrated moment right at C. That won't do exactly the same as what the 65 newtons at the end would be, but between A and B it'll be the same. So A and B will be the same. What will be different is this will be the same, but this section is just going to be a straight line, which is not what's really happening. But we're not interested in that section right now. We're interested in that angle, which that will at least start the same in both of these. So we have a case that's pretty similar to this. And that's why I had to go copy number 8 again, because this is, now it doesn't have the little cantilevered looking section on item 8 here in our list, but we're ignoring the weight of the beam, the self weight of the beam. So this doesn't do anything. If it doesn't weigh anything, there's no force out there, then it's not doing anything. So we can ignore this little section and treat it kind of as a, just invisible weightless piece out here, and just treat the beam as it looks in case 8. Now in case 8, the moment's going counterclockwise, and I drew mine clockwise, but that'll just change the negative sign somewhere. So I've got, wow, these are hard to read. Theta 2 here, this is what this says, theta 2 on the right hand side, which is the one I want. I want the angle at the right hand side. Or, well, it's not the right hand side, it's the angle where the moment is applied. That's what I want. So that's labeled as theta 2. It says theta 2 equals ml over 3 ei. So for us, theta 2 is theta b, was m times l over 3 times e times I. And they have, let me get back on the screen, they have a counterclockwise moment given a positive sign for this equation. So technically ours is going to have a negative, which just means the angle is going down below the x-axis, which it is. So we would have negative 266.5 kilonewton meters times L. Now L, you have to be careful. It is not the distance from A to C. L, now in this picture, I think L is only given in the header. Up here it says the length of what is drawn is L. So the length from one support to the other is L. So that's our 6.9 meters. Not 6.9 plus 4.1. 3 is just baked into the equation. E is the 200. Giga is 10 to the 9th. And I is 620 times 10 to the 6th. But that's millimeters to the 4th. So I have some mixed up units over here. We could either put these in MathCAD, or we can convert them over if we wanted to deal with that here. I might want to put them in MathCAD. Let's get MathCAD open and just let it deal with the units for us. Obviously on the exam you can't just open up MathCAD and I can't open up MathCAD either. Let's try the other one. That license was not working. Maybe this one will work. It's acting like it's working, but it's not doing anything yet. And there it goes. All right, so here, let's see if we can get all of this at one time. All right, so I'm not going to do the variables. I'm just going to put the numbers in. Negative 266.5 kilonewton meters times 6.9 meters divided by 3 times 200. I don't know if it knows gigapascals. Let's find out. Gigapascals times 620. Let's go ahead and do times 10 to the 6th, and that would be millimeters to the 4th. All right, so we did know what gigapascals are. Not sure why I lost my number here though. 620 times 10 to the 6th. There we go. Let's put more decimals in that because it looks suspicious. All right. Now, notice I don't get any units. Let me make that bigger. That's too small, isn't it? I don't get any units on this answer. We'll check in a second and see if it's right. But that's because it comes out in radians. So the angle measurements that you calculate using the beam deflection, they end up as radians, not degrees. So let's see what WebWork actually wants. I have this number. Let's see, where did WebWork go? Yes, it's in here. WebWork doesn't have any units, so I'm going to assume it wants radians. Oh, but it doesn't like that. And let's see. It did. And we're the same as what it calculated. All right. So that wasn't really superposition. Superposition is where you take one force and calculate the effect of that force, or whatever the thing is causing. It could be electronic circuits or anything, but in this case it's one force. And then take another case with the same beam but a different force on it, and you combine or superimpose those effects on top of one another. Here we just modified, really. We took our 65 kilonewtons, turned it into a concentrated moment, and calculated theta b, because we did have a case that looked like that converted case. The next thing it wants is the deflection at the midpoint, and we can actually get this same effect here. So we have this equation, y at the center of the span, here. It's telling us that's not the maximum deflection, but it's the deflection at the center. ml squared over 16 EI. This one will come out with units, and it's technically negative because of the way they've got it dipping downwards. Ours will end up positive because we have a negative moment compared to theirs anyway. All right, so we don't have to do anything that we haven't already done. We stay with the converted force. So the force moved over to point B becomes the concentrated moment, and we are going to use that same moment in this equation, ml squared over 16 EI. So this will be, they're using y, so let's use y, AB over 2, so the distance between A and B divided by 2 equals negative ml squared over 16 EI. So negative m for us compared to their m is another negative. L again is the length of the span from A to B, not the length of the entire beam, and that's squared. So that's where we'll end up with meters as our answer, because we have an extra meter there compared to what we had last time. 16 is in the equation. E is the 29 or the 200. I'll just write gigapascals, and I is same beam, so 620 times 10 to the 6th millimeters to the 4th, and we'll drop that guy into not WebWork, into MathCAD. I wish I could just take it over there, but I have to type it in. 266.5 kilonewton meters times 6.9 meters squared divided by actually the same denominator, just instead of a 16 it's or instead of a 3 it's a 16. And again, let's put more decimals in there. And it comes out positive because our beam is actually humping upwards there. So let's use that number, take it over to web work. It tells us to put, oh, this one does say to include units, so let's put meters on that one. And again, we got it correct. Okay. The last one it wants us to do is the deflection of the beam at point C. So this one is more superposition-y. It's a little different though because we're still using this moment. But what we're going to do is we have this, right? We have that distance, or we can calculate that distance. This distance, let's call it YC1. That distance is theta b times the 4.1 meters. This is 4.1 meters. Now, technically, it's the arc length. So this bending piece here is sweeping an arc from up there, and so technically it's an arc length. But since our angle theta b is so small, I didn't write it down here. We'll have to go look at it. But since it's so small, that arc length calculation is pretty much the exact same thing. It's just taking 4.1 meters times theta b. So that's what we're going to do. You know, technically, I guess you could also try to do a triangle there, because 4.1 times theta b is the arc length. But we could try to do a triangle trig type calculation, but since theta b's, I have not at all drawn it to scale, then it's essentially the same thing. So let's figure out what YC1 is. So if I just go back over here, there's, I guess I do need a variable there. So we have, again, it's negative because it's going downwards. I'm not going to worry with the negative sign just yet. Nope, not times 4.1 meters. So, and let's put more decimals in there. 0.0203, let's say, meters. Now that is not the actual deflection at point C, though. That's a piece of the deflection, because if we look back at our original diagram where I drew it, I drew this curving. This one, when we move that point load over from where it really is to point B, the roller, then it's not curving that section anymore. From B to C is just a straight line. So what we have to do is now let's take, and this might get really confusing, but let's put our load back on here and let this curve some more, and let's add this distance. Now, you know, I'm really exaggerating the drawing, so they're looking like they're moving to the left also, because I've really got them exaggerated. These deflections are super tiny. So remember, YC1 is 0.02 meters, so that's not a lot. So yes, it is coming inwards a little bit, but we're going to assume that that's not very much to worry about. So this, with the point load on the end, is we're going to treat like this. We're going to treat it, even though it's not, treat it like a cantilever beam with our, what was that, 65 kilonewtons? Yes. 65 kilonewtons. and our same moment of inertia, same modulus of elasticity. Now the length is just the 4.1 meters, and we're going to do a cantilever beam with a point load on the end of it and calculate the deflection at the end of that. So that's case 1. Cantilever beam, point load on the end, deflection at x equals L, which is the end of the beam, the free end of the beam, PL cubed over 3EI. So that's what I have labeled as, well, Y at C, the second part of it, equals PL cubed over 3EI. Let me make sure that's the right equation. Yes. All right, so P is the point load, 65 kilonewton meters. L is just the length of the cantilever section. It's not the whole beam. So 4.1 meters. This is cubed. And this is the same denominator from the first equation we did. So the 3 times 200 gigapascals times the 620 times 10 to the 6th millimeters to the 4th. And we will add that amount of deflection to the YC1, and that will be close. It won't be perfect, but it'll be close to the total deflection at point C. So let's put these numbers into MathCAD and see what we get. Oops, 65 kilonewton meters times 4.1 meters cubed divided by this exact same denominator. So let's just use it. And let's make more decimals. So if I add this number, oh, whoa, hold up. Millimeters to the 4th. I have meters squared here, so I've got something is not right. Oh, because I put kilonewton meters. I think I wrote that in the equation too, didn't I? That's just kilonewtons. All right. Now, 012 meters plus the 020 meters. Let's just see what those equal. This number plus that number. And maybe some more decimals. 03231. Let's see if WebWork cares for that number. Well, there it is right there. Oh, and it is negative. I didn't put my negative sign on there. Oh, wow. Can't just cut and paste from MathCAD very easy. Okay. And it likes that. So that one's not as superposition-y as some of the others, but that's a good one to work through. Let's see what else they have in here. That one's actually sort of similar. This one's, the trickiness to this one is that the point load is offset to the left, and your little reference, the point load is offset to the right. So you'll notice on this equation that the equation of the elastic curve specifically says that this equation is only good between 0 and A, so the long side. This also says that what you use for B has to be smaller than A. So I don't know if I can zoom in any more to that to make it more readable or not. It makes it blurry. But the A distance has to be the long one. And in here, that means that the A has to be J, whatever J is, 2.77 feet, even though it's on the right hand side. So you have to mentally mirror image this one to use this picture with it. So that's the only tricky part with it. Well, there is one other tricky part because it has some feet mixed in with inches, and you just have to make sure that you don't get one of your units wrong. This one's a true superposition. Let's see, still no questions in the chat, so I think we're good. I think I will not do this one. It's not a lot to this one. The interesting part with this one is similar to what we did just a minute ago by calculating the deflection here, where you find the slope at the end of C. Both this point load and this distributed load create a slope here, which don't bend section CD, they just send it upwards, and you just use the angle at C to figure out how much it bends upward, because one of the things you want is the deflection at D. This problem, if you picked one of these, you know, just one, not all 6 of them, they would be on the scale of how the hardest thing you would do on an exam 3. So make sure you go through this problem and make sure you can work all 6 sections of it. I'm going to open this one. This is closed. I'm going to open this one back up so that we can work on it some more. I didn't check to see if people have finished it or not, but since we're still kind of working on beam deflection, I'm going to open homework 17 back up. But this one would be a good one to make sure you could do, because it is one section of it, not all 6, but one section of it is on the level of a test problem. This one is just a little more complicated because you've got to divide this distributed load. Same kind of thing as that we did first, where you take the point load, move it to a moment. You take the lumped version of this little piece of the distributed load and create a moment about B. So there's a lot of little pieces going on to this one. This one's a little beyond a test question. All right. So find your teams for your Truss project. And start working on that. We've got what, 2.5 weeks? Well, yeah, 2.5 weeks left, about, of the quarter. So there's not a lot of time left. There aren't many new topics though. So there's the torsion and some pressure vessel stuff. So not a lot of new topics. And maybe we have 3 weeks left. Not a lot. There's not much left. I guess that's including this week. Don't wait too long to try to get your team figured out for your Truss project. Is probably your priority. I'm going to open up homework 17. I'm not opening any new ones because we haven't done any new stuff yet. We will get to where we are about to move into the torsion. So remember, the course is first third axial, second third flexural, last third is torsion plus other topics. And we're getting into the torsion on Wednesday. And we'll do a couple of days of torsion and then talk about these pressure vessels and kind of start wrapping things up. I have to see if this 7th is the right day. I'll have to see. I thought it was the 8th, but whatever the Monday is of the last week, that's the exam redo. The Wednesday is exam 3, and the last day, the Thursday, is turn in your report. And last bits of homework. All right, I will see y'all Wednesday, and if you're having troubles with the team formation, let me know so that we can try and form a team so that you can actually finish the project. It is a decent amount of points. If we look at the breakdown here, the design project is a letter grade, so you don't want to just not do it, probably. All right, I will see y'all Wednesday.